Last time we were looking at different ways in which we could change or upset the equilibrium. According to Le Chatelier's principle, the equilibrium is going to counteract most of that change that we impose on it. One of the things we did was with copper sulfate, with water, and then in a complex ion with the chloride ion added from hydrochloric acid. And I noticed that in the book it had a 4 written there, but I was fairly certain that it had a 6, and when I went and checked on it, it does have 6 lots of water surrounding the copper. Now, we did a similar sort of thing using the cobalt, and the one with the water around it is pink, and the one with the chloride ions around it is blue. So again, we added the chloride ions, and we made it, because we have an excess here, the system tries to use it up. As it uses this up, it uses this as well and makes that. So it goes from being the pink to the blue. In the same way, when we put it in icy cold water, we've drawn out the heat from there. When you draw out the heat from there, the system tries to make energy, and that means going from the blue to the pink, which you can see it's pink. You put it into the hot water, and basically it happens the other way around, because the system's trying to use up the extra energy that we're pushing in from the hot water. So we're pushing in heat energy in from the hot water, and the system is using that energy up. But as it uses up the energy and goes this way, it is removing the pink cobalt, hydrated cobalt ion, to make the the blue chloride complex ion. Okay. Now, the only other way we can change gases, change these systems, is to actually change the pressure on the gas or change the volume of a gas. So if we increase the pressure, we decrease the volume, and that if we decrease the volume, we've increased the concentration. There are more particles per unit space. Now, when we do this, the side of the reaction with less gas particles is the side that gets favoured. So this has got 2 gas particles, this has got 1 gas particle. If we've got that situation, it's actually going to go this way. If we're going, because we're then going to get rid of 2 gas particles and only have 1 made. So that actually favours the left-hand side. Whereas if we pull this up and we double the volume, then we decrease the concentration. So it favours the side that has most gas particles, which is this one. So this has only got 1, this has got 2, it's going to shift that way, it's going to go from the pale yellow to the dark brown. And this is shown in here. The system actually had a sudden decrease in concentration because it has an increase in volume. And when that happens, the NO2 goes up and the N2O4 goes down. This happens with a number of systems. Here in this particular graph, they've actually added oxygen. You've got a bit of oxygen here, and it's going to, because we've added the oxygen, the system's trying to use it up. So it's going to make NO2, and so there's the NO2 levels, and that's going to gradually increase to offset the problems with the oxygen. As the oxygen decreases, the NO2 increases. Okay, so the syllabus dot points, we've identified factors that can change a equilibrium if the reaction is reversible. We've defined Le Chatelier's principle, and then we've got to look at applying it to carbonated soft drinks, which we actually did the investigation for. And the carbonated soft drink has got carbon dioxide in the space above the bottle, and until you reach saturation vapor pressure, pretty much like that towel situation that you had in the last video. And the carbon dioxide is returning to the solution and going back and escaping into the atmosphere. So that's the equilibrium we're talking about. Okay, now we notice that as we increase the temperature, we decrease the solubility of carbon dioxide, which kind of makes sense if you think about it. If you have a hot soft drink and you open the lid, it's very fuzzy. There's a lot of gas that comes off it because, and much more than if it was cold, because we've got this favours the gas side, which means that the energy must be over here, because if we have it getting hotter, then it shifts it away from being the aqueous to the gaseous situation. Right, now the soda water and carbon dioxide, as I've just said, that's the first step in the equilibrium. But you notice that if you leave a coin, or in some cases a tooth, in a bottle of soft drink over a period of time, it will be worn away, or in the case of the tooth, disappear entirely. And that's because of this whole, this doesn't stop here. This reacts with the water and it makes acid rain, as you know about carbonic acid. And the carbonic acid splits up into the H plus ion that we know exists around acids, and the bicarb ion. Okay, so when we have a carbonated soft drink, it's usually very acidic, right, due to the hydronium ion that's there. Now, there's a nice little YouTube here that I haven't been able to make play. It's really worth it because it works through that complete experiment. Talks about what you did and what to do with the results, and that's really very important. Okay, now in nature, carbon dioxide dissolves in water, and that produces carbonic acid. The carbonic acid and a carbonate, we've got limestone here, that's calcium carbonate. Acid and a carbonate makes salt plus water plus carbon dioxide, but before it does, it makes the bicarbonate ion. And the calcium bicarb is actually soluble, so it kind of runs down here and drips down here, and it will land down here. And down here, there's less carbon dioxide, so the whole process is reversed, and you end up back with the calcium carbonate down here. So what's happened is you've got the rock that was here has been dissolved. Some of it will be deposited there, and then a lot of it's going to be deposited there, and it will make your stalactites and stalagmites that you find in limestone caves. Okay, now when you do your work on the soft drink, and in the recent experiments we have been doing, we've been using the molar gas volumes, directly using those numbers instead of using VM, meaning molar gas volumes. But basically that's just another way of calculating the number of moles, and the reason it works is because of Avogadro's law. Equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. Okay, and then in your book you have a number of questions, and the questions there have got answers to them, so you can take a quick look at those. There are a number of YouTubes that you'll find helpful if you're having a little bit of problem with any of those ideas. Okay, so that's the end of the dealing with the second section of the syllabus and the syllabus dot points.